Just going to say that for your final, well, I decided I'll let you bring a formula sheet. Uh, because there are a couple of too many formulas at this point of the course, they kind of build up. So it's kind of similar to what you may have seen in other math classes, like the calculus courses and things like that. It would just be like a piece of paper, you can write whatever you want on both sides. Just do it handwritten so that people actually write their own formula sheet. But besides that, there are no other restrictions on what you can put on. I mean, I still want to wait a couple more classes before I get like a sense of how much I can include on the final. Once I have that a better idea, I'll just send you like an study guide for the final. But some of you may still want to start working on what to put on the formula sheet from now. But yeah, just hands up that you will be allowed to use one. Okay, so today we still continue talking about orthogonalities. Uh, remember, like the idea of is a vector space has infinitely many bases. Now what we're looking is for bases with extra properties. So this extra property will be that it was an orthonormal basis. So orthonormal if two things happen of a vector space. So the property for an orthonormal basis was that each basis vector has length 1, right? Okay. And that if you choose two different vectors on the basis, they are perpendicular. So any two different vectors from the basis are perpendicular. By the way, I'm reminding you here that length 1, you can write it in terms of the dot product. So it's just saying that the dot product of a vector with itself is 1. So any two vectors from the basis. Perpendicular or orthogonal mean the same. And again, that's kind of like a useful condition to have because once you have like an orthonormal basis, you can decompose a vector as a linear combination of the bases very easily. So that was like the main idea for why we're after this property. Now let me explain in a slightly different way what I was saying last time. Okay, before giving you like the formula for the Gram Schmidt algorithm. So here is kind of what's going on. Let's say that you have a vector space So this is going to be a vector space of the and the dimension is going to be k. Okay. Now, when you have a vector v, basically most of what I was saying last time can be summarized in the following picture. So when you have like a random vector v, you should think about this vector making like a shadow on this vector space. Okay, so if this were like a realistic picture, this would be like the floor, right? This is like some vector in space, and literally the shadow is like the shadow, right? It would just be this thing. Okay. And when the vector spaces have higher dimensions, you cannot really visualize that, but it would look more or less like what I'm drawing right now. It's just like a generalization of that idea. Okay. So that yellow vector is kind of like the shadow vector. And the idea, like what makes this like a proper useful thing to look at is that when you look at what makes this like a shadow is that you can sort of you have two vectors here, and you can complete it to a triangle, right? That's kind of in general true. But what makes this like the shadow vector is that this triangle would become a right triangle. So that's otherwise it would just be like a regular triangle, but like the projection has a property that the orange side will make this a right triangle. What's this orange side? Well, if you I mean, it's kind of like there's a geometric or visual interpretation of like the subtraction of vectors. This orange side corresponds to V, the hypotenuse, minus the yellow one, minus the shadow. And the key property of this vector is that it's perpendicular to any vector of W. Perpendicular to any vector of W. So far, so good. Questions about this? So just to make sure this is making sense. In the actual, like as an example, in the actual case where the plane, or like where the vector space is the xy plane, right? Let's think about the vector space W as the xy plane. If you pick a vector V here, right? One like V has entries X, Y, Z. What would be the formula for the projection vector here? What are the entries?
XY0.
Yeah, XY0 is literally killing the height, right? Because you're putting the shadow on the XY plane. Does that make sense? And complement, that's actually how it's called, but the orange vector, right? Like the one that makes it a right triangle. Or if you look at this, would have entries 0, 0, Z. Right? Because that's what you get when you take the difference between those two, the white one and the yellow one. And you can see like this one will be perpendicular to any vector of the xy plane. So the formula that I'm about to give you is kind of like a generalization of this picture when the vector spaces have more dimensions, basically. And where that plane, like, that's the main idea. So if you have taken or are taking multivariable calculus, you would have seen like a formula for a projection, but that's only when there's one vector. So the vector space has dimension 1 because it's just like a line determined by a vector. So this is like a generalization of that formula to. So the formula in multivariable calculus is when k equals 1, where there's only a vector space of one dimension, which is a line. This is a generalization of that formula, the one that I'm about to give you. Does that make sense? So far, so good. Any questions about this? And here's a cool formula. It's really nice when you have an orthonormal basis. So here's the formula. The projection, and this is the key formula for today. The projection of B onto W is B dot B1 times B1 plus B dot B2 times B2 plus B dot BK times BK. And what are B1, B2, BK in this formula, or an orthonormal basis for W? Here. So secretly, this formula is saying like that you can choose any orthonormal basis, and that's true. I mean, it's not worth proving here, but like you can show. It's not too bad to show that if you had like no matter which orthonormal basis you choose, like this formula on the right hand side gives you the same vector. So it's what mathematicians will call well defined because it doesn't depend on the choice of orthonormal basis. But you'll see, it will be useful once I rewrite for you the Gram Schmidt algorithm, because in that algorithm, you just see this projection appears multiple times. So it's like a nice formula too. And again, this will be useful later on if we have time to do like least square methods or something like that. Yeah. Like in a sense, like if you thought about this, this is another perspective how you can think about this formula. If you actually thought that this represents some point, right? The point here where the two sides meet of the triangle is the closest point on the plane to this one, right? So there's like a minimization problem going on where you're finding the point on the plane closest to this point. So that's actually what's called like a Lagrange multiplier method problem, because it's like there's like a constraint, which is that this point has to belong to this vector space or plane. So that's why least square methods will work, because in least square methods you want to minimize the error, and this is kind of will like by being the closest, it's kind of minimizing something. So it's kind of like a good perspective to have, but I'll remind you about it later once we discuss it. But so it is related to calculus. That's what I'm trying to say. Like you can actually use like a find critical points of some function and you get this formula. That's another way to do this. So let's talk about Gram Schmidt. So Gram Schmidt, the idea is like it kind of perpendicularizes the vectors. Like you give me a couple vectors and I'll make them perpendicular. Like okay, so let me remind you what it said. Gram Schmidt algorithm. So again, the picture that you should have in mind is like in case we were working with three vectors, is that you would have like a vector u1, maybe a vector u2 here, and then a vector u3. So in this picture, hopefully it looks like the vectors are not even perpendicular, they don't even have the same size. But the point of running the algorithm is that the end result will be something that looks like B1, B2, and B3. Right, so it really turns them into like, makes them perpendicular to one another and of unit length. Okay, so it's like a way to like, yeah, orthogonalize vectors if you want to find a verb for it. So in Gram Schmidt, like you will start with a basis for a vector space, an arbitrary basis. And when you apply the algorithm to it, to this basis, it will produce an orthonormal basis. That's the important part. Of V. So again, it's kind of like what it does is like it creates for you an orthonormal basis out of V. Like a basis you started. So it does require finding a basis first, but once you found the basis, then you can apply Gram Schmidt. I mean, typically these problems are so long that I would just give you like a basis and ask you to apply Gram Schmidt to it. Otherwise, it would spend like an hour or something. Like it would take forever. Like they're like, you'll see that it involves tons of dot products. So that's why they're not short problems. So the formula, I mean, once we have this projection formula, the formula is very straightforward. It's just like, again, like it will involve many computations. So the first vector V1 is just going to be the U1 vector is scaled so that it has length 1. And then what the method does is kind of like, if you thought about it as like a computer program, it will store or keep track of these orange vectors that I wrote, like the ones that were perpendicular to the vector spaces. So it's kind of keeping track of the stuff which is not the shadow stuff. Like the non-shadow part of the vector is what this is going to be storing. Like I said, like, it's a sort of software. So like, for example, the second vector is just going to be U2. But now you have to delete the shadow so that you get something that's perpendicular to V1. So what's the shadow in this case? It's just a projection of V1 along, of U2 along V1. But this, once you delete the shadow, this may not have like length 1, so you have to rescale it by its length to make it of length 1. And here the projection is just, I mean, I'll repeat this formula. It's kind of follows from there, but it's just U2 V1.
For V2, right?
Sorry, yeah, this is should having V2. Yeah, good catch. Yeah. And for example, what is V3? V3 would be U3, and then you have to delete the shadow. But the shadow is now the shadow that U3 makes along these first two vectors. So let me write it this way, and I'll give you like the formula in a second. But then once you subtracted that once you remove the shadow, like you may get something that's not of length 1. And so you have to rescale it once again. And what do I mean by this formula? So the projection of U3 into V1, V2, that just means like the projection onto the plane that contains these two vectors. So it's just U3 dot V1 times V1 plus U3 dot V2 times V2. Everything's super good. And that same way you would find B4, B5, B6, until you get to VK. So like this keeps going, that's why it's an algorithm. So we just keep going until you get to that, or not, not necessarily. Oh yeah, let's put it like a VK. So the last step would be UK minus the projection of VK over, sorry, of UK. And what is this projection? So this projection of UK onto V1, K minus 1. By that I just mean UK dot V1 times V1 plus UK dot V2 times V2 plus UK dot UK minus 1 that times UK minus 1. So those are projections. So, sorry, it should have this it should have been BK, the last one. 16. So you see, like they all like if you compare like the different steps, they're all basically the same as process, the same formula. It's just that you have to as a stepping as you go further down the line, the projections involve more terms because there are more vectors to look at to take into consideration. So I'm about to do an example with this so that you see like the main idea. But are there any questions about this process? Okay, let me do an example. As I said, like this is kind of long, so I'll just do it with three vectors. That's more or less what I'll tend to ask. So because otherwise it would take for a long time. So the three that we needed are this, and this. Here's the example. So B is a vector space. So yeah, this is a vector space with bases where it is. Okay. No, leave this one because I'll revert to this one. These formulas, I'll delete those. Actually. So the problem we just asked to find an orthonormal basis for B. Okay, now let's just applying this over and over. So what is B1? B1 is B1 over this line. What is U1 is 1, 1, 1, 1. What's the length of U1? Remember the length of a vector is Pythagoras theorem. So you square each entry and add them together and then take the square root of that. Okay, so that's what the vector looks like. Obviously, I expect some simplifications on this is like the square root of 4, which is just 2. So this is 1, 1, 1, 1 over 2, which is also nicer to put the 2 inside each entry. So then it looks like this. Is that okay? Questions up to this point? So that, if you notice, it's a vector parallel to Q1, but it's no unit length. Which is again, because like an orthonormal basis also wants vectors of unit length. What is B2? Well, for B2, we need the projection. So let me find the projection first. Otherwise, this would take a little bit, it would just look longer. So the projection of U2 onto B1, right? It is U2 dot B1 times B1. What is U2? U2 is 1, negative 1, 1, negative 1 dot B1, which is 1/2, 1/2, 1/2, 1/2 times B1. So here I'm writing explicitly the dot product, right? And whatever that number is, it will get multiplied by B1, by the vector B1. So when you do the dot product, is 1 times 1/2 is 1/2, negative 1 times negative times 1/2 is negative 1/2, then the other is plus 1/2, and the other is negative 1/2. This gives you 0 times V1. And remember, multiplying a vector by the 0 vector by the 0 scalar just gives you the 0 vector. So in terms of the picture, right? If the projection of U2 along V1 is 0, what does that mean? Here's V1, yeah, it has to be perpendicular, right? So this is how U2 has to look, because that's the only way for the shadow to be a point, which is what this, or has no sense, right? If there were like an angle between these two vectors, there would be some a shadow of non-zero length. So the only way for the shadow to be 0, or the projection to be 0, is if the vectors are perpendicular to start with. Is that okay? Okay, and so for our formula for V2, what is the formula for V2 doing? It's just U2 minus the projection but I just said that this projection is 0, so it's just U2 divided by its length. And what is U2? U2 is 1, negative 1, 1, negative 1. And the length is still the same as before. It's 1 squared plus negative 1 squared plus 1 squared plus negative 1 squared. So this continues to give you 2 after you take the square roots. So U2 is 1/2, negative 1/2, 1/2. Okay. Is it? Let's up to this one. And then what is V3? Oh, for V3, we should find the projection first again, just to make it faster. So what is the projection of U3 along V1, V2? Those are the dot products, so it's U3 dot V1 V1 plus U3 dot V2 times V2, right? And now we can do the dot product. So U3 is 1, 0, negative 1, 2. Dot V1 is 1/2, 1/2, 1/2, 1/2. Plus the other dot product is 1, 0, negative 1, 2 times this vector 1/2, negative 1/2, 1/2, negative 1/2 times E2. Does that make sense? And what is this first dot product? It gives you 1/2 correctly. There's 1, 2. Yeah, well, I mean, it's fine. It's just, I think I may, compared to the PDF version, I may have, let me check. Hopefully the PDF version is fine. I mean, if not, I have to fix the answers. I just yes. Oh, I think this one should have been without the minus. Sorry. I mean, it doesn't affect. It's just I want it to be the same as the example on the PDF. Let me double check that. Otherwise, we could do it with that minus sign. But let me see. Oh yeah, it was without the minus. Yeah, no, it's not the same as it did in class, the other class. It's good, and there's a minus here, so it's good. We get 1/2 minus 1/2. Sorry, 1/2 plus 1/2. One. Yes. As you can see, these computations are not too bad in the computation itself, but it's prone to many typos because there are so many multiplications that you have to do, so many additions. So you just have to be extra careful. So this gives you 2v1 plus 0v2. So this projection is 2v1, and what is 2v1 is 1, 1, 1, 1. Okay, so in terms of the picture, it just means that if you wanted to do the picture again, to make it easier, here you have U2, here you have U1, here, like what this picture is saying is that there's like a shadow of U3, sorry, good one. This is U2, this is D1, they're perpendicular. And what this is saying is that U3 has a shadow. U3 has a shadow along B1. That's why this projection is not zero. But along B2 is actually already perpendicular. That's why the projection was zero along B2. So, but the end result is that there is some sort of shadow of U3 along the plane that contains B1 and B2. So what is our vector B3? Well, I can plug it in here. B3 is U3. U3 is 1, 0, 1, 2, minus this projection. The projection was 1, 1, 1, 1. Divided by the length of this vector. So this gives you what? 0, -1, 0, 1. Divided by 0, -1, 0, 1. Yeah. So this is fine, I think. So it should be, this has length root of 2, so it gives you 0. Let me use a color for the final answer. And that's the answer for the third vector. Any concerns? Any questions about this? It's a little bit tedious, but I mean, it's just like the formula. So the idea is that the orange, yellow, and blue vectors each has length 1, and they're all mutually perpendicular. So they are like some sort of version of the XYZ axis, but in dimension 4 because the vectors have 4 entries. So it's like a subspace of dimension 3 of R4, basically. Is that okay? Okay, yes, tedious thing to do. Now we can do something a little bit more fun, which starts with an observation. So we're switching gears a little bit, but still it's related to this orthogonality stuff. So let's start with a remark, and you'll see why I think it's useful. So imagine I give you two vectors, let's say. I give you those two vectors, right? Something simple. So what is u dot v? U dot v is 6 minus 2, which is 4, right? So that's a product between that. Now, I'm writing them as column vectors because I'm going to do this trick of thinking of a vector as a matrix, right? So if I do that, this would be a 2 times 1 matrix, right? And this one would be a 2 times 1 matrix, right? So the question would be, right? My question is, can I do some sort of matrix if you think of them as matrices, right? Is there a way to multiply these two matrices so that the end result is a dot product, so that you get 4 in this case? So can I multiply them in some way to get? What are your thoughts?
U transpose times V.
Okay, let's see. So first of all, you cannot do U times V, right? If you do U times V, it doesn't have the correct size for matrix multiplication, right? If you remember the rule for matrix multiplication, these two numbers have to agree. So if you transpose one, right? If you do U transpose, this would be a matrix which is 1 times 2, right? And B is still 3 times negative 3 negative 2, so it's still 2 1, right? And now if you do U transpose B, right? That's 1 2 2 1, so the 2's go away. This will give you a 1 by 1 thing, right? And it does give you the dot product, right? In fact, if you remember, like one time when I explained the matrix multiplication was in terms of dot products. The release was a long time ago, and you probably had forgotten that. But so, and this, I mean, it doesn't really depend on the fact that there were two entries. In general, like the idea is like a useful way to think about the dot product is that u dot v is u transpose times v, where now you think of this as an n by 1 matrix, right? And an n by 1 matrix. I mean, the fact that I'm choosing column vectors is just for convenience because when you do the matrix multiplication, the vectors are column vectors, right? But this is a very useful formula. You'll see why in a second. So far, so good. Everyone with me? So it's just like a useful observation of how you could rewrite the dot product, right? Now, this is less obvious and that's cool to do it so that you see how it will happen now. No, I'm going to take a vector. Like in this example, the two vectors had the same size, right? Now I'm going to take two vectors of different sizes. Right? One vector has U has M entries and V has N entries, right? So now I cannot take their dot products because dot product is only defined for matrix or vectors of the same. That product is only defined for vectors of the same number with the same number of entries, okay? But what you can do is like if you take a matrix A, which is size n by n, right? You can use kind of this matrix to relate the two because now you can do A times B, right? And what's the size of A times B? So this would be what an n by one vector, right? So now this vector, right? And this vector have the same number of entries. So now I can take their dot product. Okay, so what I'm trying to say is that now we can do U dot AB. Is that making sense? So far, so good. But if you look at the magic formula, right? The formula says when you have two vectors of the same size, their dot product is just U, the first one transpose times the second one, right? So this is the same as U transpose times AB. Is that making sense? So far, so good. And now I'm going to do like what's like a very clever trick, which seems very silly. This is like saying U transpose times A transpose B. That making sense? Because transposing twice does nothing, right? It's like saying 3 to the negative 1 to the negative 1. It just gives you back 3, right? So this transpose, it's like inverse, right? Like take cancel one another. So I'm not, this is literally the same as this one, right? Is that okay? But now let's apply one of these transposes to the stuff on the inside. What was the transpose of a product? It's the product of the transposes by reversing the order, right? So if you remember this, it will become A transpose times the transpose of this one, U transpose, and there's a transpose that I haven't used times B. Right, so I just kind of like use one of the two transposes to put it in to rearrange the stuff inside. Is that making sense? Yeah, I mean, you'll see the end result is kind of cute. So transpose has nothing, right? It is, so it's U. Right? So this is the transpose, like ignore this. This is something transpose times B. But something transpose times B, it's a dot product, right? So this is the same as A transpose U dot B. Because again, it's better, it's easier to start with this side. If you start with this side, when you do a dot product, you're just supposed to transpose the first factor, which is what I'm doing here. Is that okay? So let me write, this is like the search like box. So next to this property, let me put this key property. So is this actually the key property of the transpose? So what this is saying is that when you see a matrix in a dot product, you can move it to the other factor but the price for moving it to the other factor is to transpose the matrix. Okay, so you can move a matrix around on a dot product, which is kind of like non-obvious, but when you move it, you have to move it as a transpose matrix. So the matrix A can be moved to the other factor of the dot product as long as you transpose it. So this is really, in fact, you could define the transpose of a matrix as a matrix that has that property, and then you just check that it corresponds to switching rows with columns. Like it's kind of like a clever thing to do, but it's easier just to start with the definition of transpose that I gave you at the beginning of the semester, and then just check this property. Okay. Questions so far? Okay, so let me use this for something, and we'll keep talking about this next time. So this property is very useful to study the next type of matrix. So as I have said, like matrices can be like there are different kinds of matrices, like there are symmetric matrices, there are diagonalizable matrices, there are diagonal matrices, upper triangular, lower triangular. In the ranking of matrices, besides being symmetric, which is really a good property to have, and I'll tell you why in a couple of lessons. The other cool thing you could be is like orthogonal matrix. So this is one of the best things you can be in your matrix. So let's talk about orthogonal. They're also called unitary matrices. If you work with complex numbers, they would be called unitary matrices. I mean, but for us, there would be like synonyms. So a matrix U, I will call the matrix U. I would call it O, but it can be confused with the zero number. So a matrix U is unitary, or sorry, or is orthogonal. Although from time to time my mind will slip and I will just say the word unitary. So think of them as synonyms for us. If like two things happen, if it's a square matrix, which is fine. I mean, that's not like a big thing. I mean, many matrices are square. That's not the cool property. The cool property is that it preserves the dot products. Okay, and it preserves dot products. Let me write that for what I mean by that. So what I mean by that is that if you have two vectors u and b, right, and you take their dot product, that number is the same number that you would get if you do u this matrix times u dot this matrix times p for arbitrary vectors, for any two vectors u and b. So I'm just saying, like what this is saying is that doing the matrix multiplication to each vector doesn't change the answer for the dot product, if that makes sense. Is that clear? Right, so you have two vectors, you can take their dot product, if you are like an orthogonal matrix, you can multiply each vector by that matrix. You get two new vectors, right? U and UV. And if you take the dot product, it will be the same answer if the matrix happens to be orthogonal. Okay. So and I'll tell you next time. Next time we'll spend a lot of time like talking about orthogonal matrices. But for now, let me give you. I mean, how could you check this in practice, right? Because like this condition has to work for any two random vectors. So that kind of seems like a little bit too much to check, right? It's not like that you choose like your favorite two vectors in the world. No, it has to be for any vectors. So for to so there's like a useful way to check this in practice. Which requires applying the key property, right? So how can you, what would the key property that I wrote here allow you to do with the right-hand side? What could you do?
You can move the U from.
Right, like the key property says that you can move a matrix to the other factor as long as you put a transpose to it. So let's move this matrix to this first factor by putting a U transpose. So let's put like the key property here. So the key property allows us to say that U dot V, which is the left-hand side, is now the same as what you get by moving U. Is that making sense? Okay, and now if you compare these two equations, right, it looks a little bit better because now the second factor in both dot products is the same, right? So the only thing that they're differing is that U in the left-hand side is kind of being multiplied by 1 or whatever, and this is being multiplied, U is not being multiplied by U transpose times U, right? But you just have to like make a guess, right? What would make like if we had like what property of U transpose times U would guarantee this to have the same equation on both sides? Yeah, if we made that in the identity, we would be done. And in fact, since the vectors are arbitrary, you can show that that happened, like that is essentially what will happen in this case. So like a theorem says that will be that U is an orthogonal matrix on orthogonal matrix or unitary matrix if and only if U transpose times U equals the identity. Okay. And that's something that we can check, right? Because we know how to multiply a matrix by its transpose and see whether it gives us an identity or not. In fact, I mean, I'll write this next time. I don't want to do this today because in the other class I didn't have time, so just to keep the two at the same rate. But what matrix had the property that if you multiply it by something else, I mean, there was another matrix that had the property that if multiplying it by U would give you the identity, right? There was a name for this matrix.
U transpose equals U inverse.
Right, like the inverse had this property, right? The inverse had this property that U inverse times U would be the identity. So actually, this another way of saying this being orthogonal is that the inverse is the transpose, or the transpose is the inverse, which is like a cool property. So I will write it down next time explicitly so that you see it. But it is like, that's like this is the role of the inverse in general, right? So it's saying that for orthogonal matrices, if you want to find the inverse of an orthogonal matrix, you just transpose it and then you're done, which is really cool. And also another thing, what could happen? What happens if I take determinant of both sides of the equation? What would that tell me about the determinant? This would be determinant of u transpose times u, which is determinant of u squared. So it would be the determinant of u squared equals 1. So that means that our orthogonal matrix has determinant plus or minus 1. And yeah, I'll mention this next time. But essentially, when the determinant is 1, what that means is it's some sort of like rotation matrix, essentially, or basically. So just to like give you an example, when you take u to be cosine of theta minus sine of theta, sine of theta, cosine of theta, right? Which was the rotation by an angle of theta degrees. What is u transpose is cosine of theta minus sine of theta, sine of theta, sine of theta. And it's not like, it's not too bad to check that u transpose times u equals theta thing. It just uses like the sine squared plus cosine squared is 1, basically. And that's how you get it. So U is an orthogonal matrix, which makes sense because if you think about it, here's a more pictorial way to think about this. If you remember, like the dot product was just like the products of the length times the cosine of the angle, right? But if a rotation matrix should preserve the length of the vectors, and if you rotate both vectors, that doesn't change your relative angle. So that's why the orthogonality condition should be satisfied, like that the rotation would be satisfied because of that. So essentially, like an orthogonal, I mean, I'll write all of this next time, but an orthogonal matrix which has determinant 2, determinant 1, it is basically like a rotation matrix. If it's determinant -1, it means like it may have involved like a reflection, meaning that like, yeah, you just put like the mirror image, put like a mirror somewhere and like look at the mirror image of that. Okay. And then yeah, this has a lot of engineering applications for what's called hard, like I mean for these rigid objects or rigid bodies. So like there's like a theorem of Euler. I mean, once you have this equation, you can also find the eigenvalues of this matrix. We'll find them next time. And then there's a theorem of Euler that says that like a 3×3, basically that says that like 3×3 orthogonal matrix as an eigenvector. And so that's kind of the axis of rotation of the orthogonal matrix. And there are many cool things. I mean, once you know that, then there are many things you can do, like for applied problems. So these matrices like appear in many places. Yeah, like if you ever take like a classic quantum mechanics, like when you like basically the way you compute like the probability of measuring certain outcomes is by doing like a dot product. So a unitary matrix is kind of like a matrix that preserves like the probability of like the measurements take certain values and things like that. So it like they're really all over the place. So next time we'll start like I'll start from this characterization and we'll start just deriving a bunch of properties that the orthogonal matrices have. They're kind of cool to see. So yeah, so yeah, I'll see you Wednesday. And give you posted, but then later on, that's happen in the meantime. But I think there's like a good place to stop.